Hello everyone, I am Dr. Belmont and I'm going to create another video to continue the course of my classes. And this is for the Organic Chemistry 2 class, and we're going to start a new topic today. We're going to continue with our syllabus. And the the topic that we're going to discuss today are carbonyl groups, right? Something that we have discussed before in our class, but today I'm going to teach you a very unique and very specific reaction that actually I really like a lot. I think it's really elegant, I think it's really smart, right? And it's called the Wolff-Kishner reaction. So let's go and jump directly to our app in which I can draw things. There we go. And the name of this reaction is going to be the Wolff-Kishner. This is an E. Kishner reaction. Very well, and my students know that I like to resume words like reaction with an RX. Okay, what are we going to see in this reaction? Well, pretty simple. It's something like this. You're going to have a carbonyl group, right? That's what we are talking about, specifically a ketone group, right? But it can work also with aldehydes, I think. And what we're going to transform this into something like this. So first of all, let's analyze what we have here. We have a carbonyl group, right? And the hybridization is sp2. And I want to transform this into an sp3. So just because I am changing the arrangement in space, right, the geometry, I know that what I am performing is what? A reduction. So I'm adding electrons from this molecule to obtain this molecule. And you would think, okay, so what are we going to add? Like probably first electrons, probably we're going to add hydrides, probably we need something quite powerful to carry out this reaction. And the answer, surprisingly, is no. What we are actually going to use, it's something, a new compound that we haven't discussed yet, which is named hydrazine, which has this formula. Right? And KOH. Very well. And we need to add this one as a catalyst, meaning that at some time in the reaction, we're going to have to recover it. And let's not lose our mind in something that is really, really, really important, that we're also going to get nitrogen gas and H2O. So we need water, right? And we need to somehow figure out how are we going to be able to get nitrogen gas? And I'm going to do something interesting, right? I'm going to type here the structure of nitrogen gas. And most of you already know it. You have a nitrogen, you have a triple bond, you have another nitrogen, and two lone pairs in each nitrogen. So somehow in our reaction mechanism, we need to get from this thing to all of this, right? This is what we detect, this is what we have, so we need to find out a way in which this reaction can carry out with reaction mechanisms. So let's go and figure out what we can do. Let's use another new page. There you go. Again, my pen mode, there you go. So let's start with the simple thing. So I have my phenyl group, I have my ketone group, very good. And I'm just going to add some space here. More space, and instead of using anything, I'm just going to use my R, right? Because you can see that this screen is really small for organic chemistry. Anyway, so what I have is my hydrazine, right? Sorry. I have my nitrogen, my H2, and my two lone pairs. Thank you very much. So I know that what is going to happen, it's pretty simple to deduce, right? I have a carbonyl group which has a partial positive charge, and I know that the lone pairs of nitrogen are quite electrophilic, so they will perform what? A nucleophilic attack. There you go. We already know that. No news. And the next step of the reaction is going to be something very similar to what? To the tetrahedral intermediate. And we're going to have something like this. But as you can see, this nitrogen has 4 bonds, right? 2 hydrogens, one bond towards the nitrogen, one towards the other carbon. So this nitrogen is going to be how? Positive. And since this oxygen gained the 2 electrons, then this oxygen is going to be negative. So let's look first at our charges. And we have our charges balance. So we're doing something good, right? We have one positive, one negative. And with that in mind, then we can continue proposing the next step of the mechanism. And I think you know what is going to happen. So an intermolecular reaction is going to happen because it's the fastest one. So these electrons are going to pick one of these two hydrogens. And what we're going to get is something like this. Very well. And this is where things start to get a little bit tricky. So I'm going to have a nitrogen, H2, and another hydrogen, and finally a lone pair. So remember that we had in mind, we need to get in mind that we need to reach what? A triple bond between nitrogens, right? And the only way in which I can do that is if I transform the double bond, the single bond in this intermediate, right, here, between nitrogen and nitrogen that is single to transform at least into a double bond. And the only way that we can do this, right, is if we first create a little bit of what? Of water. How are we going to do this? Well, we have to play with the charges. Imagine we need to reach somehow water. And at this stage, the only thing that I can think of, right, is that maybe these lone pairs will go in here and create a double bond between the nitrogen and the carbon, and hence, what is going to happen? We're going to have a leaving group in the form of what? Of an OH. So let's see what we get. We would be getting exactly like this. And this nitrogen is going to be positive plus what? Plus OH minus. So if we check the balance of our charges, what you see is that we have a positive charge, we have it here, and we have a negative charge, which is here. So the balance of charges, we might be getting something. But look at this. The nitrogen, this nitrogen, doesn't like to be positive, and we have an OH, which we know it's a good base. And we need to reach what? Water, because it's something that I detected at the end of my reaction. So the only thing that I can think of is that this negative charge goes and pick up this hydrogen, and then what we would have is something like this. New page. There you go. Pen. Thank you. So what we will have is N, H, lone pair, lone pairs, plus what? Plus H2O. Okay. Very well. So now what are we going to do? We already have created one of our byproducts, so we are in the correct track. And we need to follow up with something that may make the electrons move, right? There's no way in which we cannot just continue like this if we don't propose anything new. And let's remember that we still have what? An OH, okay? And something that might happen is that we need to create what? Nitrogen gas. So we need to create somehow, right, a way in which some of these electrons create what? A double bond in this position. And the only way that I can do that right now is if I use the OH that I had, right, to attack what? One of the hydrogens of the nitrogen, creating the next intermediate. Very well. Plus H2O again. And now we have what? A negative charge that is conjugated to a double bond. So something that we can propose that will happen is something like this. The electrons of the nitrogen will create a double bond between nitrogen and nitrogen, and this is going to do what? Move towards the carbon. So what we will get is something like this. And 2 electrons here, and a negative charge. Excellent. So we have a carbanion, right? Plus what? We still have water. So these carbanions are powerful bases, right? And they don't like to be like that. And look at this now. This carbon that is here has something more similar to what? To an sp3 configuration. And what do we have now? A double bond. So we're getting closer to perform what? Well, first of all, the creation of nitrogen gas and the reduction of the sp3 carbon. So we are getting there. We need to add now into this sp3 carbon what? A hydrogen. To perform the reduction with an acid-base reaction, what we're going to do is basically something like this. So what I will get is now something like this. And we are getting close. Plus what? Plus OH negative. So you see, we recover our OH because I am only using this as what? As a catalyst. Very well. So just for you to see the level note here. And let's go and use a new page. There you go. My pen. Here it is. And the structure in which I was working with is this. Now I have what? My hydrogen. Now I have what? My nitrogen. My double bonded nitrogen. Another nitrogen. Attached to what? To the H. Very well. And my R. Sorry, I think I forgot to put the R's there, but it doesn't matter, you know what I'm doing. Okay. Very well. So, what do you think is going to happen next? Any suggestions? Well, I still have what? The OH negative, right? And something similar might happen again. I can go, pick it up, and then, right, make these electrons push towards, right, the other nitrogen to create what? The additional double bond. So we will have two double bonds, one single bond, so we will have a triple bond. And when that happens, then these electrons can move towards the carbon again. And let's see what we will have. So I will have my aromatic ring, my R, my negative charge, my electrons in the carbon, right? And the nitrogens. No nitrogens. My hydrogen that I had reduced before. So this hydrogen is this hydrogen plus what? Nitrogen gas. Plus what? Plus water. So what do you think is going to happen? Well, we have a carbanion, which is a powerful base. We have water, and we need to recover what? Our KOH. So very simple. This is going to perform an acid-base reaction. Good. And what we will have is our compound plus nitrogen gas, and we recover our catalyst. So I'm sorry if it's a little bit messy, right? But currently I'm working in a way in which I can draw better reaction mechanisms. Please, I hope that you find this useful. Please send me any comments that you think I can use, or suggestions I can use to improve this experience. And I will see you soon with another video as soon as I can. So be patient, please. Thank you and goodbye.